We'll have Owain and then James, and then we have a special presentation from the Republic of Korea. And you are welcome to remain for all of those presentations. I did request that you keep your presentation to about 20 minutes with 10 minutes question and answer. We have specific work items on with regards to AI and machine learning, with regards to the use of 4G and now 5G. We've done technology reviews and IMT 2020, and we have a new technology to be presented as well. So thank you very much. And without further ado, I'd like to get going. I'm just going to say I am happy to attend this meeting. It's being recorded, so just to let everybody know it's being recorded. Welcome both to Owain and James, and to anyone else who's joined us specifically for this session. We have people online and people physically in place at IALA meetings. This is the presentation session for Working Group 2 of the IALA Navigation Committee. Now, that's an interesting picture. I can see you, Ernie, now. I used to see everybody else, so I'm not quite sure what you've done.
Wait one.
Okay, we'll wait one just before we get going. I don't want to take up too much of your time because I am really looking forward to these presentations.
It seems as though we've lost the screen.
You've lost the screen completely?
Yes.
Okay. Do we need to get?
Yeah, no, it's that one that's tripped. They have to go back and reset it on the main system.
Okay, so apologies for that. It looks like we're going to be a minute or two going until we get on the main screen, because everyone has to be able to see you. I mean, your presentation. And they want to see you too, Owen.
Yeah, that's fine. I'll just quickly test sharing my screen as well, just so we can.
Yeah,
get
please
that
do
over
that.
there first.
Yeah, please do that.
All good.
That's all
That
good.
works.
Perfect. Yep. And James, did you want to practice test sharing your screen too? I'm sure it'll be all fine. It's all fairly straightforward. We're very good at this by now, aren't we?
I'm assuming it'll be absolutely fine.
Yeah, good. So we'll just wait until they can reset the camera. That was really interesting. It was working fine. Is it the click share, Ernie?
No, it's the actual camera and screen and everything.
Best laid plans. Almost there.
It appears that all the screens are off.
Oh, so it's not just us. I guess the other option is everyone can just log into the meeting and we can just put your make sure you're on mute, and so we don't hear you, and we could just do it all online.
Give us one more minute. It may just be a power switch.
Okay. Well, you all had your cup of coffee, so I'm going to have my tea.
What sort of tea are you
Natasha,
going
I
for?
can see you. It's lovely. The camera's right on you right now. It's been so long since I saw you. It's a real pleasure.
I know. I thought you'd be here this week.
I did an ESG assessment and a safety assessment. We're never sure what Australia is going to do.
Yeah.
So from my environmental sustainability review of my activity as a company, and also the ongoing issue with COVID, I made the decision to stay here for this set of meetings. I do plan to go to Rio though for the conference.
Okay. Were you involved with BTS as well last week?
BTS, yes.
Yeah.
Yes, so I did. I was the same room actually. I chaired the. I was assisting. Stefan was officially chairing because he was there, but we did the personnel and training working group.
Okay.
Yes. So we're in the final review of the output documents, the new VTS training and the new VTS on the job training. Two documents, two big documents. It feels really good if we can get them through plenary this week. It's tomorrow. If we can get them through. We started this in South Korea, I think at VTS 46, and this is VTS 53. So you can imagine how long it's taken.
We found the.
You're coming back.
We found the faulty switch.
Okay. So I might have to ask for your indulgence. We may go a few minutes over. I do want to give Republic of Korea their full 30 minutes as well. Ah, hurrah, looks like we're good.
Yeah, we just got to wait for Google to take over our screen.
We have the right camera image. That's a good sign.
Yeah.
And I see some wonderful familiar names online. So Frederick, good to have you with us. And Mike Card, nice to see you. You give us a thumbs up when we're ready to go. Eh bon? That does not look like a happy face.
It's the silence that's quite unnerving.
It is. It's gone really quiet, Ernie. It's gone really quiet.
Yeah.
It's
Is it 7 o'clock at night where you are?
Yes, it is. Yes, yeah. I have
Right.
2 other meetings after. I've got this one. I've
There
got
we
2
are.
more afterwards. So
We're,
Are we on?
We're essentially back online, and we're just closing down all the alert screens, and we'll be able to go.
excellent. And we're still recording. So when I do this, I'll cut this part off, obviously.
All the fun bits. Right.
Isabel, we see your best side.
Yeah, I'm sorry.
That's okay. I'm just teasing you. You can see we're very formal, Owen.
Should be okay now.
Fine.
Yes, thank you.
Okay.
There we are.
Okay. Woo!
There we go.
Excellent. A bit of a clap there. Thank you so much. And thank you everyone for attending this session. It is being recorded. I do know there's many people who wanted to attend as well and they're not able. So thank you very much I will pass to Owen first and then we will go to James. Owen will speak to us about AI. James will talk about IMT 2020 on buoys, and then we will get the presentation from the Republic of Korea on their import paper. So Owen, over to you, and I will disappear and listen.
Great, thank you. I'll just share my screen here. So yeah, hello everyone. Thank you for the invite, first of all. But yeah, essentially, I'm Owain Brennan, the Managing Director of SeerBI. So we're a business focused on the real application of machine learning and artificial intelligence within organizations. We do have a current focus on the maritime sector, although we've worked on other projects outside of it too, mainly in heavy industry around IoT and things like that. But again, onto those projects afterwards. So we're a team made up of ex-university data science researchers, essentially people looking to apply the technology that's for far too long been locked behind research or made to feel unreachable by huge organizations. So we work as a data science agency to build tools with data science capability, machine learning tools, or AI tools. And we're also building our own internal tools to make the entire data science process much more efficient when we're building it for other organizations and for ourselves too. We're also developing some products that we're looking to integrate within industry and release to the wider market. So we have a lot going on, a lot of really interesting research happening. And today I'm going to walk you through kind of a bit of the background of SeerBI and how we work, a small introduction to artificial intelligence just to help people who haven't got a full grasp of it so far, and some of the really interesting work we've been doing on ship detection with artificial intelligence as well. So to start off, I will quickly walk through our team. So yeah, first of all, there's myself. So I say Owain Brennan. My background is a master's in data science, after which I worked as a lecturer in data science, as well as in multiple maritime organizations like PD Ports, Casper Shipping, and the High Tide Foundation. I've worked on several technology projects from IoT to supply chain optimization, onto healthcare analytics and lots of different areas. And I essentially have a focus on bringing data out of silos and into cross-pollinated areas where data can be examined and utilized and not locked away in these little cages. We also have Hannah, who's my co-founder. So her background is in international development, and she works on many projects as a project manager and yeah, heads up a lot of the machine learning projects, making sure all the staff are working and have the right end goal in mind. And we also have Amelia, who is our head of data. So Amelia's background is in computer and data science, and she's also worked as a lecturer before joining us and taking her research into industry and applying that research. So we have a very specific approach to data science because it's very easy to get lost in machine learning and AI. Our approach is made up of 3 main stages to ensure that we can reach the right solutions. The first of these is problem understanding. So in this stage, we work with universities, industry, or other stakeholders to understand the problems that industry is facing. And we do these with industry call-outs where every 2 months or so, we'll go out to industry, try to find the most pressing problems with industry, and yeah, see what they are facing. We then move on to data understanding. So we start to look around the problem and see what data is actually available and start to understand if a data science solution is actually a viable solution for the problem that is out there. Because sometimes the data might not be ready yet, the industry might not be ready for a data science solution. So there's no point in us tackling these problems that we can't actually solve. And then finally, we move on to our data science process. So this is where we start developing real solutions, be it data analytics, machine learning, or AI. This process ensures that we're aligned as a team and that we understand the problems that our teams are facing, which is a vital aspect to get really efficient application of AI. And usually why the application of machine learning and AI doesn't work as well is people don't understand the problems, or they don't understand that the data isn't ready, and they jump immediately to let's apply the most fanciest technology that we can rather than taking the time with the process.
So just 1 second, Owen, just to confirm, the reference of VTS there is Vessel Traffic Services, our same reference for VTS acronym, is that correct?
VTS, sorry, yes.
Thank you.
Yeah, Vehicle Traffic Services.
Oh, which that? Yeah, Vessel Traffic Services.
Yes.
Yeah.
So some past projects we've worked on as SeerBI within maritime and kind of outside of as well is we've worked with the Port of Tyne. So we were invited by the Port of Tyne to be part of their 2050 Innovation Hub and advise on how data science and machine learning can play a role in their 2050 strategy, which aligns with the UK Maritime 2050 strategy. This involved collaborating with several organisations and stakeholders to understand what data they have, how it can be used, and how it can support their future strategy. We've also worked with Casper Shipping, where we looked at automating the UK customs process, again, using data automation, saving hundreds of man hours within that organisation, and preparing them for a wider machine learning driven process. And then one of the most applicable for this talk is the work we've done with Connected, who work as a IoT and asset intelligence organisation, looking at using computer vision and using sensors to detect things that are happening in ports. And this is where our research into computer vision and AI for ship detection really began, with our work with Connected. So a lot of the work we originally did with Connected was based around LoRaWAN networks and satellite providers like EchoStar Mobile, who we work with to develop in-port communications where traditional communications weren't available. And again, we're looking at applying these satellite LoRaWAN-based technologies with the computer vision technologies that we're developing too, but I'll come back to that in a second. So with all of our projects we work on, we have strong technology partnerships with the wider industry. So we work very closely with NVIDIA. So those who don't know, NVIDIA are the largest machine learning hardware developer. They do a lot in software too, but most of the machine learning training and the machine learning inference, or applying the model onto a place, is done on NVIDIA hardware. We're also a Microsoft partner, so we work with Microsoft's technologies, be it Azure Cloud, to build our technologies. We again work with Amazon Web Services to host and build our technologies. And we are part of the Net Zero Industry Innovation Centre, which is based in the UK. We work on a few different projects with them in terms of IoT and carbon capture, but it kind of backs up all of the work that we do within Net Zero. So before I move on to kind of our exact use within VTS, I want to give a bit of a background so that people understand what I'm talking about when I say machine learning or artificial intelligence. So there's a diagram in the middle here, which kind of shows you an outline of how machine learning, neural networks, and deep learning all fit within artificial intelligence. As you can see, artificial intelligence is kind of the thing that encompasses all of the rest. Artificial intelligence is essentially any intelligence that isn't inherently sentient. So anything that we can make do something without it knowing how to do it already. So this has been done for years. This artificial intelligence isn't a new thing. We've been teaching computers how to compute large numbers or decode messages for years, like the work done by Alan Turing in World War II, which he himself referred to as artificial intelligence. So AI isn't really the new fancy bit. It's everyone thinks it's the deeper bit, but it's kind of on the outside. We then have machine learning, which is the process of introducing an algorithm to data and allowing it to learn based off of what it's exposed to. So this is usually what people think when they think of machine learning. You show it something and it will learn how to do something. So this is where most of the recent advancements lie, and where and this has been made possible due to the vast amount of compute power that is now available and the research that's been done by some amazing people in the industry. Within machine learning, we then have the bit where my main interests lie and where a lot of the work that SeerBI does, which is neural networks. So this is a specific type of machine learning that looks at simulating how the brain works in terms of its synapses and replicating that within a computer to try and train the algorithm. So it's a very specific style of machine learning neural networks. So it's commonly used in things such as computer vision today. And then finally, we have deep learning, which is where we begin to string together many different neural networks to create a real brain structure in a more complex algorithm. Although this is highly inefficient right now, but it's becoming better all the time. It's one of the really new aspects of machine learning that everyone's trying to apply, but no one knows the best way to do it yet. So we focus most of our research on the neural networks, which have been locked in locked in research that we can apply to industry instead. But all of these complexity can really be broken down into three main fields of machine learning. So there's only really three things that machine learning can do and will do. These are classification, prediction, and regression. So classification is if we expose an algorithm to data, it begins to recognize the patterns within that data, or it begins to recognize a specific object that we've taught it to recognize when exposed to new data. This is used commonly in things today like computer vision, ads targeting on Google when you get targeted ads, that's classification, or personalization in things like Netflix when you're given a recommendation for a movie. That's all classification style machine learning. The next is prediction, which is quite a common concept. Most people can understand prediction. It's predicting numbers and the next number in a sequence. This could be stock market analysis. It could be predicting stock levels in stores, setting sales targets. It's an easy one to understand that. And then there's regression, which is the idea of finding a statistical link between different variables within a data set. So this is used in things like weather prediction, or it can again be used in sales targets to see how one effect affects another variable. So yeah, most of the machine learning algorithms we use today are either distinct one of these or a mix of these three, but most machine learning can be broken into those points. We then have the machine learning styles. So these are styles that we can use to solve any of those three problems, the prediction, classification, or regression. Any of these machine learning styles can be applied. So supervised learning and unsupervised learning. Unsupervised learning is where we show data and data labels to an algorithm that give examples of inputs and the desired outputs that we want to see. By showing the algorithm enough examples in the right way, we get it to replicate the process that we've introduced it to. So in this style of machine learning, much more work goes into the preparation of the data, understanding the data bias, and understanding what we're putting into the machine learning to see what we get out. Whereas in unsupervised learning, which is where we introduce neural networks and deep learning, so where most of my interests lie, in this case, we give data to an algorithm with much less instruction, but allow it to adapt itself to the situation and to the data that it sees. In this kind of style, much more of the work goes into the design of the algorithm itself rather than the data that goes into it. So designing what that brain structure looks like, designing what the output's going to look like. So I say both of these styles can be used throughout prediction, classification, and regression, but it's useful to understand what these are. So now I'd like to walk you through, now we kind of all have a bit of an understanding of machine learning and artificial intelligence. I'd like to walk you through one of our most recent problems that we faced and solutions we designed, and specifically how it fits into the talk today. So the problem that we looked at was see the title here, it's a very data science title, it's not very fancy. It's the use of synthetic images to train computer vision models for the detection of ships at ports. So for this problem, we looked into the identification of ships in port environments in order to support the current VTS and GNSS systems. We took learning from similar systems in the automotive sector, so systems that are used for autonomous driving by companies like Tesla, and introduced some new cutting-edge technology that has to be applied in the maritime sector due to the differences between driving and port environments. There are very specific things we had to do. In this case, we looked at the introduction of synthetic data to train the computer vision model, which I'll go deeper into in a second. And we took learnings from lots of previous researchers who worked on a similar problem. Researchers like Park et al. In China, who developed the deep sort algorithm to detect ships in high movement situations, such as on cameras attached to buoys, and Wu et al., who developed ship detection for fast inference on an algorithm named SFMF. So we looked at a lot of their research and drew a lot of learnings to ensure we weren't just ignoring the past research that was done, but really applying what has already been done in industry and then trying to improve upon it too. So we had three major key findings before we went into the advancement of our solution. Again, this was all done during our data preparation and problem understanding and data understanding phases. So these main key findings that we had were that the current go-to technology for ship positioning in ports is not in line with the advancements we've seen in other sectors, such as the automotive sector. We also found that the YOLO CV, which it stands for You Only Look Once computer vision architecture, is currently the go-to computer vision model for many cases, such as fast machine learning model training or inference in industry. So this gave us a good baseline. And then we also found that the text-to-image synthetic machine learning models have very recently advanced to the point of very high image quality generation. So this gave us 3 points to move forward on within our research. So the first part of the project looked at, as I said, computer vision. So computer vision itself is a combination of both deep learning and convolutional neural networks in order to allow a computer to classify what it sees in a camera. And you can see the image on the left there. You can see bounding boxes, drawing around people, cars, traffic lights. So these are things that are being detected. And the research that's been done recently has led to lots of breakthroughs in computer vision, so it gave us a good baseline. It's used in industry today, for example, in things like autonomous driving, fault detection, translation. And in the diagram on the right, you can see our process for computer vision. So we have our input data, so images that we have collected. We have signals of, these are kind of the tags that we've applied to them to say what a ship is, what a ship isn't as well. We then go through the data processing phase, so removing missing values, having specific time windows for the videos and images that we collect, and standardizing the data to remove as much data bias as possible. And this is the phase we also introduced synthetic images to have as little data bias as possible. We then go through the training set as well. So we have a test data set that we keep to the side to test the model and evaluate it after it's done. And we have our machine learning model training, you can see there, and I can go into more detail on that later on if you'd like. We then have the synthetic image part of the project. So due to very recent artificial intelligence breakthroughs by OpenAI and Google, people are now able to generate very high quality new images just from text. So these models take in, understand regular text that's been written to it, and output a brand new image that's never been seen before at a very high quality. So these images have the advantage of being very high quality, which makes them a good use for computer vision model training, but they also have the advantage of being able to generate edge cases. And this is where the main crux of the research and our application happened, because we can generate images of ships doing things that we don't have examples of happening in real life. So ships hitting into each other, ships in positions or from angles that we can't usually get angles and images of them from. We can generate these cases using the synthetic images. It's very high quality, but it does introduce an aspect of data bias, which is a large part of the ethics of the research we're looking into now. So here you can see an overview of the system design of our computer vision model. So some of the technologies we use in the system design, DALI 2, which is the image generation model that we used. YOLO V5 is the computer vision model baseline that we used, and CVAS, the tool that we used for image labeling. And you can see some of there's a bit of, again, data science view on what we did there, but essentially starting with sourcing a set of images of real ships, generating synthetic images of ships, labeling all of these images, splitting the data set into multiple different ways. The really interesting part of the research again was that we created 5 different data sets and 5 different machine learning models for this project. For the first machine learning model was using 100% real images. The next one was 100% synthetic images. Then we had 25% synthetic, 75% real, 50% and 50%, and 75 and 25 the other way as well, which gave us a good understanding of how the synthetic images were really affecting the machine learning model. So I said the first process of this was collecting real images of ships and generating images of ships. So for the first phase of this research, we only collected 700 images of ships, which we collected from the website Kaggle. So Kaggle allowed us to get many different images of ships from historical photos, CCTV, cinematic images, and this allows the system to learn and be used on many different quality of camera systems, not locking it to a specific hardware. And then, as I say, we generated the images of the ships as well. And then within here, we labeled all of the data. So the data all had to be manually labeled, looked at by a human, so they could say this is a ship, this isn't a ship throughout all of these images, which is a bit of a painstaking process, but it has to be done. And then we move on to training the models themselves. So I'd say the technology we used to train the models was, we introduced PyTorch here, which is a machine learning framework. YOLO V5 was the base machine learning model that we retrained to detect ships. We used NVIDIA and AWS, their compute space, to be able to develop these models as well. You can see the different sizes of the models in the middle there. To data scientists might understand this bit a bit more, but you can see the brain structure of the neural networks within there and the different sizes. Essentially, a bigger model will be more accurate, but will require much more compute power to be able to allow us to run the model on it. So we use the middle ground, which is the YOLO 5 M, which gave us the capacity to train the model, but also when we run it, we can run it on hardware that ports might already have available, which was an important part of this project. So yeah, in the end, we ended up with our 5 machine learning models of the same splits of the data sets that we created. So now the interesting bit to me, we've got a bit of fancy math going on. So to be able to see how well the models perform, there are lots of different metrics we can use. These can be precision, recall, loss, efficiency, but the best one to use for a case like this is average precision. So with average precision, we can look at essentially how precise it is at analyzing all of the images that we tested it on. And as you can see here, our results that we found were that the worst performing model had a 75% average precision, and that was the 100% synthetic model. So, which makes a lot of sense because it wasn't ever trained on real images of ships, so it doesn't perform very well on detecting real images of ships, but it gave us a good baseline to work off of. And then we had the 25% real, 75% synthetic data set. So majority it was made up of synthetic images that had 78% precision. Then we had the 100% real data set, which again is a good baseline for us to test. Next up on the accuracy, we had the 50% real, 50% synthetic, and the best performing model of all was the 75% real, 25% synthetic data set. So essentially what all of this means is that when we introduce some synthetic images to training a computer vision machine learning model to detect ships, it has a higher accuracy than when we don't introduce synthetic images to the training process. So this gave us a very good baseline to work off of and a good hypothesis as well. But what we also found is that when you introduce more than 50% synthetic data, the accuracy of the model and the precision of the model starts to decrease, which we don't want. So next steps for this process, we are going to start looking at the further breakdown of these real and synthetic model positions. So not just looking at these 25% breakdowns, but down to 10% breakdowns to really understand the effect of the synthetic data. We'll look at multiple object classification on the model itself. We're going to look at, we've nearly completed the end-to-end ship detection on the ships. We are adding detections to a 3D space, which is currently ongoing. So we're working with NVIDIA to do 3D scans of ports to put these detections into a place. We're looking at sending detections over LoRa network as well. So that's the work that we're doing with M-Connected, is sending these detections, not the videos themselves, but the detections over LoRa, so we can do machine learning on edge in an isolated area. And again, linking these systems, taking the data out of silos and linking the data with current GNSS API development and on and off-site hosting. I was hoping to fit in a bit of a demonstration, but I think I've gone a bit over there.
How long will the demo take?
I can show you a completed demo. I don't actually have to run the model. I will see what I can do.
Because I think it would be really interesting to see the demo.
Yes, I have one.
And you do have about 8 minutes left according to my clock.
Okay, I will. Well, I have one that a video that we tested it before. This isn't a. So usually when we run this model, it will sit on a static camera. So this was a test that we did on a moving camera to see how the model performed on it. But here you can see in this video what the model output will look like from a static camera view. But again, this will feed into much more complicated systems, but it will take a bit of time to open that demo. But I'll run this for you now, and you can see how the detections work. Again, an unoptimized view of how it might look, testing different angles here to see how the detection will work.
Interesting to see the detection with the containers. It looked like it was detecting the containers and then the ship.
Yeah, so see, I say usually with these models, we'll have multiple static cameras around a port that we'll use rather than a moving camera. So this was a test we did, but it worked quite well, we found. Yeah. And the numbers that are coming up on the side there is the confidence that the machine learning model has that is a ship. So we can use these parameters to, again, understand what the machine learning model is thinking and draw the knowledge graphs within here too. Yeah, that is, right, there you are. So yeah, I know there was quite a bit of a rush at the end there, but I'm happy to answer any questions you have on the work that we do.
Thank you very much. We do have time for some questions. So I'll put that out to the floor before, of course, I have a couple, but I thought I'd put it out to the floor first. Any questions for Owain? Yes, Jaime.
Yes, thank you, Owain. I have seen that firstly you put that you will rely on imagery and in GNSS, and after you as a next step you address the GNSS a GNSS backup. I was wondering, what kind of backup for GNSS you are considering.
So the work we're doing with NVIDIA right now with GNSS is, so that's the kind of, it links into the 3D modeling of the ports. And so when we're looking at 3D modeling of ports and linking in these computer vision systems, we're looking at bringing in the GNSS data, bringing in our detection, and as many other inferences as we can on where a ship is to get a real-time accurate location of where the ship is itself. So a lot of it is going to rely on the 3D model of a port that we're able to generate. And we're working right now on that with T-Sport as well.
But any particular system as completely backup of GNSS?
Sorry, yeah.
Yeah, so it was addressed that as a next step to look at other means to compute the navigation position, the navigation and the position solution of the ship. And you are looking for another type of system for position. And my question is, what are you looking for precisely as a system which is completely independent of GNSS?
So our systems aren't trying to be completely independent of it. It could be in the future with, we wouldn't rely on our entire systems being completely independent of other systems that are out there right now. The system we're looking to build and is working right now on Teesport is a backup to the systems that are there currently. The future of the systems, when we have much more highly accurate detection, end-to-end ship detection, that's where we'll look to replace the current GNSS systems. But right now, we're looking to work very closely with providers to look at that end-to-end positioning within a 3D space. Well, that answers your question.
And I just wanted to follow up on that, because from the GNSS and from our discussion on Sunday, you were saying that you're not actually reliant. So if the GNSS does fall over, you still have that 3D modeling of the port, and you still have the ability to provide the accurate positioning based on that other data. So it's not 100% reliable, relying on the GNSS. You have other, in the existing models that you have.
Yes, exactly. So we can do it without right now, but we're not looking to replace. So it's again, with our research, we look at working with as many data systems as possible, not cutting out data systems to try and replace them. Yeah. Okay,
thank you. Ernie.
I have two questions. The first one being, when you say you model the port, how far outside the port you go? In fact, do you look at the entire port approach, let's say 5 or 10 nautical miles out the port, along with all the aids navigation to the actual port, or are you actually just looking at the port infrastructure? So that would be question number one. And question number two, if you were looking at the confidence level of detecting an actual vessel, we noted that some of the confidence levels were in the 10, 15 and 20%. And what would you consider to be a confidence level that would be similar to human intelligence?
So for the first question, so we just look within the port itself, so with the port infrastructure. We're not currently looking at outside of the port, any nautical miles outside, but again, it's something we can look at after we've developed and within later stages of model development. In terms of the confidence score, so the confidence score you saw on one screen there was using a single camera to understand the confidence that the machine learning model has. When we apply these models onto a port itself, say you'll have multiple cameras pointing at one ship, so you'll have multiple confidence levels from multiple angles to understand if that is a ship or not. So when we're looking at the confidence, it's not just of that one view. We look at adding every single camera view that we have of a ship and giving that a score. For the baseline of that, it depends on, we can adjust it per port on what confidence they think is acceptable for their system, or we can work with trust to start understand what will be the industry standard, because there isn't a standard right now. But personally, I'd say above 60%, but there isn't currently a standard of what is classed as human confidence. It really depends on what the industry starts to accept.
Thank you.
All right.
Thank you. And just before we move on to the next question, just to clarify that one. So back to the first question. So the port infrastructure, so out to the edge of port limits, would it be the charted port limits? Okay.
Yeah.
And then that second one, the cameras that you use, so as you know, ports use a lot of CCTV. I expect these are special cameras, or can you actually take data from existing cameras and feed that into your system?
Existing cameras. So we don't look to work with any specific hardware, and that's kind of the point of our systems, is that and the reason that we use lots of different images from different styles of cameras and historical photos is we're not trying to lock our software into you using specific hardware. Instead, it's creating a system that works with any current cameras. You can install the system and it will work. There's not a huge procurement process happening. CCTV.
Thank you. I think we have time for one more question, perhaps. Ernie, you already had one. I'll see if I've got a moment for any other questions online. I will come back to Ernie. Well, I'm going to take the chair's prerogative, and I do have a question. You talked about the different learning styles and the specific, the supervised learning and the unsupervised learning, with a very brief overview of those. what are the issues and benefits, in a quick summary of each of those, and which of those do you think is the most appropriate for this type of operation within a maritime environment?
So for this type of operation, currently it has to be unsupervised learning, as to be able to do computer vision. Right now, it relies on neural networks, and because we are inferencing so much data at once, the benefit of unsupervised learning is that it can understand and it can take in much more data at a time than supervised learning machine learning models can. So because we're taking in video, because we want to do the inference in real time, we kind of have to use unsupervised learning. There are advancements happening in supervised learning that will allow us to reach the point at which we can do video at scale on it. And there are cases where supervised learning can introduce better accuracy, better precision in a real-time environment due to the fact that we can feed it the data we want to feed it, and we can tell it exactly what we want it to do at the end. Although with the current technology that's available, computer vision has to rely on the unsupervised learning, again, due to the amount of information, video, and the real-time analysis that we want to do.
Okay, thank you.
Okay,
I'm looking at the time. Ernie, is it a pressing question? Do you want?
No, I'm happy to answer it later or ask it now, as you wish.
How about we spend some bit of time, and I'm also, at the time that you were doing your presentation, Owen, as I mentioned, we are working on an AI guideline, and I've sort of put a few little hooks in there where I might want to follow up with you on that.
Yeah.
And thank you again very much for your input.
So
a virtual round of applause for Owen as we thank you for that presentation. We're getting some actual applause happening. Oh, I don't have my camera on. You can't see me right now, so I am here. Thank you so much for that. I would like now to move to James' presentation. So James.
Thank you ever so much, Owen. That was fantastic. I just don't want to have to follow that, to be honest, if that's okay. So
I'm sorry you have to. No. We're very interested in what you're doing as well with the work that you're doing with these. We've done a lot of review of IMT and 5G, so I'm looking forward to this. Thank you very much, and I'll let you introduce yourself.
Okay, fantastic. Can you see me okay?
Yes.
Super.
We can see you, and we can hear you, and we see your presentation fine.
Perfect. So I'm James Thomas. I'm the CEO of Jet Engineering System Solutions. We're building 5G networks that float. We think there's a lot of different rationales behind this. So it's safety, security, sustainability, and operationally, there's benefits. So I'm the CEO and the founder of the business, and we've been going a couple of years now. So I'm just going to take you through a little bit of that journey and what we're working on. And yeah, if there's any questions, that'd be great. So 5G, just to give you a bit of thoughts here on 5G. There's a lot of buzzword about it, and it's a lot of bull. And not many people actually really need the use cases of 5G. If we think about 5G on land, we're hearing about it being very much around faster, more data rates across each of those sort of big sectors. But actually, it's really different in our use case because we're trying to enable comms where comms doesn't exist. And the really interesting piece with this is that if we take the city centre, there's a lot of work on saying we can do things quicker, or we can do medical health, or we can do all these amazing things. But actually, there's a lot of risks here that actually don't apply to us because we're doing it very differently. So we're looking at 5G because it enables each of these things: a safer, secure, sustainable, smart operation. So I'm sure you're well aware of a lot of use cases of why comms at sea would be very useful. So I was a sailor. I started out doing a race called the Fastnet, which you may or may not have heard of, crossing the Irish Sea and back on a little yacht with no comms because the engine had failed, and we were sat there with radios going, okay, this isn't great. And we've recognised that actually it's not just us in pleasure vessels that have this problem. It's the renewable sector that's getting further and further from shore. It's the drones that could go and maintain those renewable assets and monitor them. It's the autonomous landscape. It's the smart ports, the runway to the ports. It's sea safety, it's aquaculture. There's a number of operations that sit across those pieces, and the use cases are quite huge. So in renewables, there's no comms for the first 3 years of installation, service and commissioning. That's about 300 people at sea continuously with limited to no communications, which isn't a very safe environment for those seafarers. In terms of drones, we can look at actually using drones to go and monitor blade erosion. Wind farm blades last not that long if it's rained. So go and monitor them with a drone rather than a ship. That makes it a lot more sustainable. We can look at the smartness of the operation. So aquaculture is a really good example of this. The thing with aquaculture is that there was an algal bloom that lost £1 million of crop in one go, and they didn't know that the bloom had come through. So actually being a bit smarter how we do things has a lot of real tangible values. So when we look at telecoms, we're very different to 5G on land. We're not in a city. We've not got thousands of people. We're not trying to do things faster. We're doing it really differently. When I say that, it's not the same use case in the slightest. It's completely polar different. So in the city, that medical health thing is super low latency. It's super fast comms, masses of high bandwidth. We're not there at all. We're doing something very different with this 5G. We're off grid. We're low density and we're reliable. But we are long range, low bandwidth. There's a lot of different things that flow into this. And the reason for that is that at sea, there aren't actually that many people, even that 300 people. It's very different as a sort of as a solution. So our solution is a mesh of buoys hosting base stations. So you can see our test rig at the front there and our little demo kit at the back. So the test rig is a floating base station. We can deploy it in ports, harbours, sort of those protected environments. It's about 6 meters tall, so it's moderately sized, but it's still fairly small for our oceans. That's there to sort of start to show the scale of the journey we're on. We've launched these and proven these, and the thing we've proven that's really exciting with 5G is buoy-to-buoy communications. With 4G and previous generations, we can't do that. Now we can. We've written quite a lot of proprietary algorithms to enable the buoys to talk in the manner which you can see on the screen, and at high speed. So range is one aspect of this, speed is another. So range is actually possible to get up to about 22, 25K between each buoy, so it's not actually a very dense network. It's a trade-off with bandwidth and other bits there, and reliability. The other piece that's exciting here is the data rates. Again, we can use different spectrum for different data rates, anything from sort of 30 to 300 megabit a second. So huge amounts of data should we need to. And when we think about that, 300 megasecond is the sort of level of data that you can't get with SATCOMs and you can't get in cities most of the time. So it's a hugely powerful tool. Sorry for the cough. So we started out building use cases. So we built the little box on the left. That was our little first comms box that we built. And what we were doing is we were doing some sea safety testing. So we put some buoys in the water with some weather sensors. So nothing really that special, but connected it over a 5G standalone network. The exciting bit there was the data rates we could achieve. And that's what the box on the left did. It managed data over 5G and it proved that we could connect. We had a reliable connection. We did 120 days continuous service without a single dropout, which is kind of a cool factor to say is actually we self-recovered, self-healed and built a network that floated. We then went and looked at what the use case for this was. So we've done some work with aquaculture. We've done some work with some other bits and pieces. So aquaculture is exciting. Again, it's cameras, image recognition. So we've got 2 cameras focused on the target. We then do some AI on the target and look at the growth of the aquaculture. There's a number of different other applications for AI. And I think one of the exciting things for us is we're very much the enabler of that technology to be possible at sea, rather than having to be land-based. So almost all those applications can be further and further from land, which enables actually to make use of a lot of those technologies. But that was a use case. So what we did was the little buoy in the center was talking to the big buoy on the right, which was talking to the shore. So we could then relay comms around the ocean. So buoy to land, which means we can now get that hopping of the network as we grow it. all whilst running at the several hundred megabit per second, because that was 2 raw 4K video feeds we were doing in real time. So we started to build some applications at the back of this. So one of the applications was looking at actually what's the idea of the buoys, what's the locations, what does this sit like, what does this go into. So we built the web application on the right for the 5G Royal Dorset team. This was just some early mock-ups of what we were building, but what it was all around putting that data live on a screen. So we built the live dashboard of this data to show actually the use case for this, and this was working with the project partners there, included the RNLI. Now, as we go forward, I think one of the things that's exciting for us is welfare and well-being. I think it's something that's not talked about is actually the emotional challenge of probably being at sea continuously for days on end without talking to your loved ones. And even if you get a window of actually I'm coming into port, I've got 3 days now I'm in the North Sea, or I'm coming into the Western Approaches, I'm nearer land, I could talk to my partner now, because from the Western Approaches up to sort of Hamburg or up to into the Baltics, it's still several days before you'd probably get decent connectivity. With our solution, we can start to get that a lot earlier for the seafarers, which means that that welfare piece and that overall emotional well-being will hopefully be improved. I think there's a lot of smart operations here that we can start to do. We see that across the 2 things, the ports, the wind farms, the 2 major ones. Whether it's big data or autonomous robots, simulation, some of the cybersecurity, there's a lot of different things and use cases that can become possible because of the data. And without the data and the connectivity, a lot of those you can't fundamentally do. It's brilliant to know where your ships are on the runway into a port from land, but it would actually be better to know it when they're actually needing a target vessel, something to go and maneuver those ships. So that's one of the things we're looking at, is how do we enable further from shore applications of Industry 4 and almost creating an Industry 4 at sea. I think the thing for us is that this has got to be sustainably driven. And there's hundreds and hundreds of use cases that stack together to create the sustainable solution. We're looking at what sensor packages we host to create those data streams that add the most value. So is that camera feeds? Is it carbon dioxide feeds? Do we want to know what the methane emissions are? You know, what's the data that really adds the most value? So we're doing a lot of research into that at the moment, as well as building the core technology of the floating base stations. We found quite a few things that we're looking at with ports. This is mainly idling vessels, emissions, water quality. There's also they're the green use cases. The personal welfare are the people in the sea itself. You know, in terms of like the tug vessels, the pilots and VR piloting, you know, and then there's the efficiencies enabling of this and the security. I think actually one of the biggest things we've seen is this high level of idling from weather delays, and the impact of that. And the other piece that we've seen is the fact that almost all shipping is on the same route globally, and ignoring the piece in the middle of the oceans because they're doing the same thing for several days at end, where almost all of the maneuvers and challenges happen are closer to land than we recognize normally. So it's that final sort of 50 to 200k coming into shore where we're trying to sort of look at reducing that congestion on the routes and helping with the sort of the wildlife elements there as well. We started to build data dashboards on this. So what we've got here is that this was a project that we're looking at for a customer, working with a DFT to look at actually, if we plot all the data overlay from all the buoys that we're going to be putting at sea, what can we do in terms of port capacity docking, vessel docking? What does that dashboard look like that enables a far more intelligent port and a port operation? And I think the other piece here is actually that, how do we get that runway to it? You know, that offshore tracking from AIS, which is brilliant in the middle of the oceans, and all the way in. What's the way to try and assist with the smoothness of that transfer from big data at sea through into the land, where we look at actually the number of these operations that are in very congested areas. The other side for this is offshore wind. Again, there's some very big use cases. Apologies, I think we've got the wrong slide on here. But the offshore wind has got very much a similar set of requirements, except they're static in the middle of the ocean where they have no comms for that installation period. Or once they've installed, they can't use those other technologies because they've got no connectivity between the wind farm and shore, because they've got a fibre from the wind farm back, but they're often a gap between the two. So it's filling in those gaps in the ocean. I think one of the things that we've looked at is actually, it's great having wind farms that are green, but actually what's the amount of infrastructure that's out there that's enabling those green installations, and what's powering it currently? What can we do with comms that can reduce that impact, and how can we make it substantial impacts there? So if we take a single drone going and looking at a wind turbine blade, that could reduce that ship. And some of those wind turbine blades last 3 years sometimes, and you're going, okay, that's a 200-meter blade made out of where it's glass fiber and wood core that's lasting 3 years, that we don't know quite that lifespan, and we're sending ships to go and send people up that asset to go and look at and maintain. With comms, we can do that so much greener and cleaner, and that's just one of the use cases that we see within that environment. I like to show some of the team sometimes. I think it's important to see who we've got. So there's myself, Martin, Chris and Dave on the board, and then we've got Duncan, Izzy, Vicky and a few others that are in the delivery team, in the leadership. Would love to open the conversation up to see if anyone wants to speak to us. Depends on who's important in the conversation there and what the right person to speak to is. But more than happy to open the floor to anyone in that regard. There's a number of us, whether it's the commercial implications, which would be myself and Martin, whether it's the operational delivery, or whether it's actually how do we make this more environmentally sustainable, which is more likely to be the Vickies and Erin's, or the people that are on the page. But yeah, we'd love to get in touch and keep on the conversation following this presentation. So thank you ever so much for the chance to present. There's mine and Izzy's email on screen if that's of use. And really good to get the chance to present to you today. Thank you ever so much.
Thank you very much for that. And thank you for keeping well within the time that I had requested for you. So thank you so much for that. Are there any questions for James on the presentation that's just been provided with this concept of the use of the 5G at sea? And just for your information, James, we've done some review of this 5G activity in the past as well. Did I see a hand raised? I can't actually see everybody. Yes, Jesus, please.
I was wondering about the power consumption of this equipment that would be placed on the ATON equipment. Have you some experience on that also?
Yeah, so we've done a lot of power systems modeling to work out what size the power of the asset needs to be. And we've got the challenges that globally that changes depending on how far north we are or south we are. So for example, off Scotland, we need a much more solar, we need much less wind, and there's a model we've built. So depending on where the asset gets deployed, we've got a different solution almost, but we've got a fitted 4-knot width. So it enables us to scale that quite quickly. There's a lot of challenges in the platforms themselves and making them sustainable as possible. It's all off grid. There's no fossil fuels. We've not got a generator set running continuously through the winter or anything like that. We're going to top it up with fossil fuels. This is all off grid, which is solar and wind.
Thank you for that. Do you actually have a power consumption figure that you work towards? Not your result as to how you manage that power consumption, but what might be the actual consumption?
Yeah, we're looking at under half a kilowatt.
Under half a kilowatt.
Yeah, which is running an entire base station at sea and edge computing. So we can do a lot of those really big data problems at sea and process that there. So that's a hugely powerful platform that we're putting together. So the platform that we're trialing probably in 2023 Q2 is going to be it's either the 12-meter or the 22-meter mast on a 12-meter disc. So it's a huge buoy that we're looking to build to go and actually try and run edge computing at sea.
Thank you for that. Very interesting. Any other questions? Yes, Wusong.
Yeah, thanks for your interesting presentations. As I understand about the 5G as a standalone, we can find some use case of 5G SA in a smart factory. So we can use that 5G system in some kind of inside the building, right? So is this the same case on the use of A2N, like a smart factory?
So in smart factories, it's small cells. And on a small cell, you've got low transmit power and you've got very high frequency. It's almost like indoor Wi-Fi plus on steroids. You know, you've pumped the Wi-Fi full of crack and it's going for it. We're very different. We are low bandwidth. We are very long range. It's a very different construct of how you use the standards of 5G. What 5G SA gives us is the ability to do something called integrated access backhaul, which means I can get my buoys to talk to other buoys. So we spent a lot of money developing software that enables the buoy to talk to other buoys without a fiber optic cable between them. And that's the really powerful piece, because in the factory, you have fibers running around the factory to connect all those radio cells together. We can't obviously do that around our oceans, because that's obviously going to have a massive impact on the ocean, which we don't want to have. So we're doing that all over radio, which means we have to transmit and receive on the same antenna set.
Thank you for that. Any other questions? Yes, Ernie.
So if we had to take this technology and move it away from buoys, but to traditional infrastructure around a port and along a coastline and still use the same technology, in other words, no infrastructure required to the remote base station, would that still be a feasible way to go forward?
So we are looking at how we give away content on land. What we want to do is work with our safety and security services. So in the UK, we have people like the RNLI that obviously are very, very influential bodies. And we want to try and give connectivity to people like that are doing positive use cases at sea. The need will be for infrastructure deployed at sea, however. You cannot just have 5G on land because you will not get the range. So to cover those complex sea basins where there is a lot of activity, you will need deployed infrastructure. Where we're working is to minimize the deployment of infrastructure because it's a cost, it's an asset, it's going to have a hard life. What we've done is we've created platforms that are suitable for the environment, that have the biggest range and the best possible use of that constraint possible. So if we look at a coastline, and I don't know how familiar you are with the North Sea, everyone, I'm assuming most people understand where that is. We've got a wind farm that's about 100 kilometers from land, 180 if we're talking the Dogger Bank. I can get comms from land to maybe 30 kilometers from shore at most. After 30 kilometers, there is no comms. So we need to relay that to get that to that wind farm. That's the job we're trying to do. We're not trying to replace on land comms. We're trying to be that hopping out to the complex sea basins.
There's one more question from here, Gillian.
Okay, what's the question? Yes, please go ahead.
Just thanks for that. It's really interesting, James. In terms of the work you're doing with the RNLI, is that around base station sort of AIS transponders, sort of infill areas, or is it just for monitoring the vessels and things like that? What sort of work is it?
With the RNLI, we were on the Royal Dorset project together. They were the project supporters. So they were aware of what we've been doing. What we're trying to do is we're trying to move to a way, we need places on the land where we deploy infrastructure to get that first hop to going to sea. We'd like to make sure that was in places where there were a lot of tourists, a lot of people in the water, so we could give away some comms to try and make that area of the sea safer. That's what our intentions are. Okay, because I mean, for the MCA, because I work for the MCA, so there might be some use case here for us in some of our difficult areas that we've got where we're struggling to get mission planning for mast towers and things like that on land, but to extend the range of some of the infrastructure. It's one of the things we've been talking to a number of ports with is actually it's easier for ports to put buoys in the water and plan to put buoys in the water than it is to actually pop up masts on land, because they own the seabed there, because they've got the rights to deploy into it. Because the issue we have around the UK coastline is that most areas are
covered by, sort of in areas of natural sort of outstanding beauty and, national trust and heritage sites and things like that, we struggle to get permission to, even put something else on an antenna, that already exists there. So it seems really interesting. So I'll probably touch base with you offline around this.
That'd be fantastic. Thank you ever so much. If you're from the MCA, you're probably aware of the MAAT program as well, which might be of interest.
Thank you very much. We do have a question from Ms. Koo.
Thank you, Chair. It's very interesting, and then I personally appreciate jet engineering to show the 5G use cases. And then I wanted to comment that actually I could assume that the jet engineering might have many difficulty of implementing those solutions, because available 5G solution on market provide the limited capability compared to what a 3GPP now is working to develop the more enhanced enabling technology. So I think 3GPP can provide more enabled technology which help the jet engineering enhance those solutions to implement the more rich features. Thank you.
Thank you, Ms. Koo. And James, just for your information, Ms. Koo is the representative from 3GPP at the meetings that we have here, and she's continuing provided us with updates on the work of 3GPP through the different releases. Thank you for that.
Great.
Yes.
It'd be great to connect, Ms. Koo. I'd love to see how we could work together.
Thank you.
Are there any other questions? I can't see the hands raised. I can see a very narrow view of the room right now. I do have a question myself, so perhaps I'll put that forward because I was looking at the range that you provided, which is the 22 kilometer-ish. I think you mentioned there 30 seems to be the maximum you've got, and the data rates that you have. So my question is sort of linked to that, but on a bit of a vision that I have. Would it be possible to use the ships as part of your network to help you with that jumping off that are in the area, especially where you have a lot of ships in the area? I know it will have a link on the range, but also ultimately I'm looking at this concept of crowdsourcing data for specifically weather data, with thinking about the El Faro and the Livestock 1 issues that came out. And the fact is that they didn't actually have the local weather in the area at the time, and it was a very tragic loss of life. So I know that there is a specific action out of the El Faro, which is regarding this ability to get more data, more up-to-date weather data. So it's probably a bit of a dream yet, not there. But what are your thoughts with regards to increasing that mesh network that you've got and making use of the other platforms, the other resources you have out there, being the ships?
So in terms of, each of the buoys is going to be fitted with a wind profiler. We're looking at putting vertical wind profiling in every buoy. So we've got probably the best weather map of each of those complex seabeds in the world. That's going to be really powerful. The second piece of your question, I think, around using ships, I think there's some challenges with using ships because we've got to uplift so much in terms globally to build that infrastructure piece. And one of the things we recognize is that has a huge cost, where it's got limited benefits in so many areas of the world. With the way we're looking at things, we don't see it being an overburdening number of bits of infrastructure to connect those seabeds. So I think we looked at modeling what the North Sea would look like, and we did about 100 buoys across the entirety of the North Sea to pretty much fill in all the blanks, so there's connectivity across the entirety of the North Sea with either 4G or 5G, if we worked with partners like Tampnet. And when you think about that, actually less than 100 buoys is really not a huge amount of infrastructure to create that hugely beneficial experience. By putting it on ships, I mean, there's thousands of ships globally that would need the uplift. They would all need to be working on the same standard. We'd need to have our patented software on each of those ships. And whether we'd want to operate our business in that manner would be another thing, because that would be a challenge. We're offering data as a service. We're not offering system sales.
Okay. And it's just interesting that you said there about the buoys in the North Sea. So the practical seafarer in me, the simple sailor, is thinking, okay, so how are we going to navigate around all of those? So it's another aspect and marking. I remember when wind farms came out, I was working at Ayala and we set up a guideline on the marking of wind farms. I can see that we're going to have some challenges, I think, perhaps as we get more infrastructure with buoys in the water having an impact.
I fully agree, and I think that the interesting thing is that's why we've looked at maximising the range between these. At 20 plus kilometres apart, this is going to have a small impact comparatively to wind farms, which have got a huge amount of them out there already.
Okay. Very interesting. Thank you very much. Are there any further questions before I let James go? You actually have 2 minutes left on your 30 minutes. So,
Gillian, there's one more in the room.
Okay, yes, please. I will go to the one in the room.
Thanks, Gillian. Thanks, James.
Could you speak up a bit louder, please?
Sure. Just in relation to the number of buoys, James, and obviously you've been deploying them all as special remarks up until now. Have you considered adding the hardware to existing aids navigation?
I think, yeah, I have considered that. I think what we would love to do is work with the providers of the aids to navigation, so these could become aids to navigation, and put the two bits of kit onto one asset, because that makes it a lot more environmentally sustainable. It makes it a lot better. The challenge we've got is the amount of power we're drawing is just so specialized. It would need to be quite a collaborative project, I'd imagine, to move that into a traditional aids to navigation. Again, opening ourselves up to this formula, this is one of the things we'd like to work with, is what's the best solution for everyone here rather than just us. But yeah, the bit that's valuable and the bit that's hard to do is the power management and the software. That putting it on different floats of different colors is absolutely something we're more than happy to work with.
Thank you very much. An excellent question, Owain. I should have thought that one myself.
Thank you for the excellent questions.
Oh, thank you so much, everybody, for your participation. It's been great to have you here, James, and Owain as well. I think we're ready now to move on to our final presentation of the day, which is the presentation from the Republic of Korea. Now, I think just to confirm with the presenters from the Republic of Korea, are you happy if Owain and James want to stick around to hear that, or I can't see the screen? Are you happy for the guests to stay, or would you prefer for them to go before you do your presentation on the input paper?
Yeah, the speaker of this input paper is Hee-jin Kang from Sunnyweave Tech. Please.
Hi, Hee-jin. Hello, nice to have you here. So my question before we start the presentation, yes, hi, me, I can see you very closely. We need to move. The camera's moved. Well done. Are you happy for the guests to stay for your presentation, or is this something that you want to say in a closed environment?
It's okay. You both can stay here.
Okay, excellent. Thank you. So I will pass the floor then you, James, if you need to go, you're welcome to go. But if you're able to say, James and Owain, you might find this interesting as well, the work that's gone from the Republic of Korea.
I'm going to have to drop off, but thank you ever so much for the incredible questions, and hopefully keep in touch with everyone. I'll put my email in the chat.
Okay. Thank you. Thank you very much, Owain.
As well. Yeah. Thank you all for your time. And yeah. Thanks a lot.
Thank you. Excellent. That's wonderful. I'm really looking forward to this presentation. So I will pass the floor over now for the presentation from the Republic of Korea on the import paper. So please, I hope you have the ability to share your screen. Is everything okay?
Let me try. I'm a guest. Can I share?
Yes.
I believe you've checked into the Teams meeting, is that correct?
The IATA expert is sitting right next to her.
Ah, fantastic.
Oh, yes. Okay. Okay, let me start the presentation. Thanks for
Yes.
giving me this great opportunity to introduce the technology called MS Wave. I'm Heejin from Republic of Korea, and I'm very honored to be here at ILA to introduce this technology. Today, I'd like to introduce this new innovative technology step by step. So let me go through problems to solution with some related technical explanations. Before we start, let's watch the video that is overview of the MS technology.
Perfect and strong communication, even in metal environments. Introducing Sunny WaveTech's MS at MS solution, which made the impossible to possible. The problem of communication failure in previous metal environments has been the cause of major accidents in hazardous industrial environments, such as ships and process chambers. Sunny WaveTech has finally found the solution to the existing pain point from the magnetic field. MS at MS communication technology succeeded in enabling strong communication and transmitting and receiving accurate data, even in blind spots where communication was not possible. By generating a magnetic field on the surface of the metal. Through several years of empirical research, Sunny WaveTech implemented the world's first IoT product, Aurora 1.0, which can customize and monitor the data you want to see, such as internal and external sensor data of the ship in real-time audio and video. With Aurora 1.0, it can be applied not only on ships, but also in all environments surrounded by metal, such as chambers. What is so different compared to other products? First, simple installation work. It can be easily attached anywhere on the ship to exchange data conveniently. As shown in the video, you can experience a new communication environment just by attaching the Aurora product to the surface. Second, fast and innovative communication. High-speed communication is possible up to 1 kilometer between APs based on Wi-Fi, and regardless of the thickness of the bulkhead. Communication without deviation is possible in any direction. In addition, convenient and smooth communication is possible through the mobile network on the ship. Third, desired data collection. It is the only metal communication that can monitor desired sensor data like vibration and temperature in various forms, such as real-time video and audio. Fourth, strong security and clean communication. As the only communication that utilizes a magnetic field, it does not generate noise or interference, and eavesdropping is impossible unless it is tampered directly, so it has stronger security and uniqueness than existing communication products. The world's first flawless IoT technology with sensor data provides a new wave of communication beyond guaranteeing security. MS at MS Solutions will take a revolutionary leap forward with your business. Waves flowing on the metal surface. Sunny Wave.
As shown in the video, there are many problems with existing wireless communications. Have you ever experienced that the phone call was off when you were in an elevator? Probably most of you have experienced this uncomfortable situation. Like elevators, if the space is surrounded by metals, it limits wireless communication because electromagnetic waves cannot penetrate metals. In industries, limitation of communication causes critical issues related to safety as well as work efficiency. So we need advanced technology to solve these problems. This is why we are introducing MS wave communication. MS wave communication is an innovative system that uses metal surface wave technology to get rid of limitations of wireless communication. MS stands for metal surface at magnetic substance, which means this new technology needs metal surfaces for communication. And we call the products and the total solution that use the MS wave technology Aurora solution. The idea is simple. As you can see in the picture on the right-hand side, if you put the resonators on the surface of metal, those two resonators transmit data to each other through the surface of metal. The device contains sensors to measure any types of data, and then the device transmits data to a PC using an AP along the surface of a metal. There are four main products in the Aurora solution: a resonator that generates MS waves, devices that measure data via connected sensors. The types of sensors are adjustable depending on the demands of users. The device can communicate in the form of MS wave or of existing radio communication. There is an AP that works as a bridge of data transmission and a monitoring software for monitoring the data. The unique technology of MS wave communication was introduced in journals. The paper on the left-hand side is from IET, and it's about resonators. And the right one is from Scientific Reports, and it is about power transmission using MS waves. One of the authors of the papers, Hak-Sun Kim, is right here next to me. So he will answer technical questions at the end of the presentation. MS wave communication can overcome limits of radio communication in metallic environment. As you may know, there are many shadowing zones in ships because majority of rooms in ships are surrounded by metals. And this new communication system will resolve existing network problems. And MS wave communication provides solutions for energy efficiency. As introduced in the Scientific Report paper, not only communication, but also power transmission is available using MS waves. Also, since it is a harness-free technology and only needs environment that has continuous metal for communication, this helps reduce cost of installation and maintenance. Since the whole body of the ships are made of metals, the body of the ship could be the best medium for MS communication. In chapter 2, let's learn about metal surface wave, which is the base technology of MS communication. Just like the wireless communication technologies, MS wave communication follows the third and fourth Maxwell's equations, which are the conventional wireless theories. This means that technology of MS wave communication is not totally a new idea. That you may wonder what is new and why it is innovative. As we know, electric field is reflected or absorbed by metals. However, we needed to think outside of the box to overcome the problems, and we found the solution from the Gauss's law for magnetism. It states that magnetic field lines never begin nor end, but form loops or extend to infinity. And this was the base idea that we started researching surface waves that flow through the metal and develop MS communication. MS wave communication was developed from the conventional wireless theories, and it also follows the evanescent theory. An evanescent field is an oscillating electric and magnetic field. Please look at the first picture on your right. An electric field is generated in the direction of z-axis. As explained in Maxwell's equations, magnetic field is generated as an electric field is generated. Because the direction of these two are perpendicular, magnetic field is generated along the xy plane. In our case, xy plane is the surface of metal. Then, the power of MS wave can be calculated by the Poynting vector theorem. Also, as shown in the second picture, the evanescent field away from the surface attenuates rapidly. Since the field attenuates much faster than the wavelength, metal surface wave communication allows fast communication. As said, the theory of MS wave communication is not new. There have been related theories out there, but it wasn't applied to the communication system to overcome limits of existing wireless communication. This miracle cannot happen just with those theories, but MS wave resonators make this possible. The structure of the resonator is shown in the picture on the left-hand side. A dielectric is polarized when an electric field is applied to it. At this point, an inductor is needed to store energy in a magnetic field to generate MS waves. So at the bottom of the resonator, a slot is inserted and it has a periodic pattern. The pattern is for adjusting a frequency band depending on users' demands. Like the picture in the middle, when the resonator is attached to the metal, it converts the electromagnetic signal to a magnetic signal, and it transmits the field along the surface of metal. The picture on the right-hand side shows the result of simulation. When signal is penetrated along the z-axis, electric field is generated along the same axis, and H field is generated along the XY plane. Here are videos of the simulation results. The video on the left-hand side shows how it resonates when it is attached on a metal substance. But when the resonator is attached on a non-metallic substance, like the video on the right-hand side, it does not generate any waves. Since this is a totally new type of communication system, there have been some frequently asked questions when we introduced this technology. First, some asked if the performance of MS wave communication is dependent to metal types. Well, MS waves are not generated on diamagnetic materials. Ferromagnetic and paramagnetic materials have a great environment for MS wave to be propagated as they are magnetized. Especially ferromagnetic substances like steels, nickels, or cobalts are the best because their relative permeabilities are much bigger than one. The second question is related to the first one. Do you think paints on the metal affect the performance of communication? Well, it depends on how thick the paints are applied to the metal. Paints are dielectric substances which cause magnetic resonance and decrease communication power. So if paint is thickly applied on the metal, it will affect the performance of communication. The third question is about power spectral density of the resonators. When we performed the EMI test, we found that the power spectral density of MS wave with Wi-Fi is lower than 2 milliwatt per megahertz, which is lower than spectral power limitation. Now let's see the cases of maritime domain. We have conducted tests in various ships. The cases that I'd like to share to you are listed on this slide. We have tested the products at an aluminum tugboat, a steel tugboat, and a steel ferry. Basically, tests were conducted to prove the concept by analyzing the performance of the communication in different situations and validating the communication distances of MS communication. Tests have been conducted with equipment shown in this slide. All these equipments are for data transmission or analyzing the performance of MS wave communication compared to radio communication. For the first case, as shown in the pictures, we have installed devices and APs on the boat and checked and compared the performance of MS communication and radio communication using the resonators and wireless antennas. As shown in the picture on the right-hand side below, and at the far right corner of the picture, we set the store as a base point of the task and installed an AP and a PC to monitor the performance of the communication. Then, we installed devices and another APs at the mast, the void space, the engine room, and the steering gear room. Then, the devices transmit data to an AP installed at the same room in the form of either MS waves or radio signals. When AP receives data, it sends data to the AP that is installed in the store. Then you can monitor the data and the performance of communication on a PC. Let's look at the graph on the left-hand side. The MS wave communication speed of data transmission between the store and the mast is about 2 times faster than the radio communication. However, the results from the other rooms show big differences of performance between those two communication systems. The transmission speed of MS communication in the SG room was the slowest among the MS wave tasks because it was farthest room from the store. For the case 2, as similar to the previous case, we installed an AP and a PC at a base point. At this time, the base point was the bridge. The devices and other APs were installed at the bow store, the bosun store, the warehouse, and the engine room. At this time, the performance of MS communication was 10 times better than the wireless technology. Compared to the previous test results, this shows that the performance of MS is much faster in steel tugboats than the aluminum one. We also have checked if MS waves are interfered by any other communication systems. We measured the noise generated when the engine of the ship is on or off, because there are communication equipment running during the time. As you can see in the table, there is a difference of noises in between those two states. However, compared to wireless, MS waves have pretty constant noise. Also, as shown in the picture on the right-hand side, we have installed devices and AP at the engine room in different spots to analyze performance change based on the installation location. As a result, there were no big differences overall between engine on and off. In ferry, we have tested performance of MS communication in different distance conditions. We installed an AP and a PC at the point where the blue star is pointing. And the device and another AP were installed at a green star point and moved from 1 through 4 to see the performance difference depending on distance. Through the distance test, we have found that the MS communication works over 100 meters in straight distance. Since there are curves and additional routes, the real communication distance is much longer than these results. Based on the results of previous test cases, we have proved that the MS wave technology can be applied to maritime communication. So we have been proceeding 2 cases of pilot applications. For this, we have installed Aurora devices in 2 different ships. Both cases are for measuring data in a ship and capturing the real-time data with a corresponding monitoring system. Also, we are monitoring the real-time status of the ship with camera and Aurora products. Most ships are made of metals, and metals interfere at wireless communication. So lately, there are demands for communication in ships to observe real-time data generated in the engine room or in other facilities, or just for video or voice calls with people. However, there haven't been any technologies to perfectly resolve these communication problems. And now, Aurora is the solution that makes communication possible all over the ship. Although metallic walls can be a medium for communication, you can just install Aurora equipment on metallic walls and let them communicate for monitoring the real-time video, like the security camera, and data measured by sensors. Aurora is compatible with existing wireless technologies such as Wi-Fi, Bluetooth, Zigbee, or LoRa. Even though we have only tested with these 4 radio technologies so far, Aurora is also compatible with any of communication networks such as LTE or satellite. The existing radio communications don't work in metallic environments, but MS works perfectly. Therefore, Aurora will be the best communication solution on ships. We don't just collect and display data. As data is collected on database, we can apply AI to learn, analyze incoming data, and give feedback to users. This will help to command and control the environment of ship. To wrap up, let me summarize today's presentation. 1. A technique called MS wave is based on the theory of metal surface wave. 2. Its total solution is called Aurora. 3. Our products can be applied as RF-free in marine domain, where radio communication is hardly applicable. 4. We are still acquiring and analyzing meaningful data by testing and applying our products to various ships. 5. We'd welcome any of your guidance for the optimization, promotion, and application of MS wave technology on ships. Lastly, we'd like to invite the committee and other related corporations to work with us to efficiently apply Aurora products to overcome remaining wireless communication problems in maritime domain. Well, that's all I have for today, and thank you so much for listening.
Thank you so much. That was very interesting, and I can see some really intriguing applications for it. I will open the floor right now to questions. And perhaps you could stop your sharing of the screen so we can see a little bit better. Yes, Jaime, go ahead, please.
Thank you for the presentation. I see it's very related to internal onboard communication, to more or less like a very sophisticated UHF to communicate, and it's really solve a lot of problems, mostly, for instance, in cruise ships, maybe where the crew members there is a lot of crew members, a lot of people on board the ships, and if there is any eventuality, the coordination between the crew members is essential. But I just wonder if there is a business case that could solve some challenges in the area scope. I mean, from shore to the ship. And I think this will be very related to the coverage area, no, of this solution. And just to know if there is some test not only on board ships but between the shore and the ship at the end.
So that's right. So we introduced the MS wave technologies inside the ship, and then inside the ship to the shore or outside, we can connect with the LTE or 5G.
Okay.
So public network. So if you wanted to use the outside network, and then we connect the gateway to the ship, and then inside we collect all the data, and then connect with the outside is the gateway, okay, or internet. So we can show you that the outside here we can see the situation of real time inside the ship. So
let me share the screen.
Certainly.
So I'm remotely controlling the PC installed on a ship. Devices are installed on a ship, and this is a vibration sensors.
There's inside we install the vibration sensor in the ship.
You can see the vibration of the on board ships in Korea in real time. You are seeing.
Also, there are cameras here. So we installed cameras at an engine room, and this is a real time.
You need to send someone to walk down there so we can see them.
I can control the camera using these things, like moving the camera.
So that means that from the camera to the main system installed on board, on their route, we use the MS communication, and then the transfer some streaming data to the LTE and through the internet, and you can get its image at here.
Do you have calculated the latency between what is happening there and what you can see?
Yeah, this system, this MS currently use the Wi-Fi band frequencies.
Okay.
So there are a few latency. Okay. It's the same level of the Wi-Fi system. But the highlight what I want to highlight at this time, that MS communication is radio-free system. Do not use any radio, just to use the magnetic wave. So we don't produce any interference to the another radio systems, and vice versa, right? So that is the and then we can get very high speed, over 30, 40, even 100 megabps without any using radio system. That is the main characteristic of this system. So you can use this system inside the ship, and maybe a wind farm or any ocean plant, something like some environment surrounded with metal. Still,
or a lighthouse for remote monitoring.
Yeah.
Or a lighthouse for remote monitoring if you have enough metal in the area.
You can use on a buoy, made by steel.
Thank you. We have a question from Ernie.
Thanks, Julian. I haven't been an officer on a ship for a long time, so forgive me if my knowledge is really thin. But on new ships, there are ASIPods, and ASIPods have huge magnetic fields with very high transient noise profiles that are in the magnetic domain and actually go into the gigahertz domain in a magnetic layer. And depending on where the generator is for the ASIPod and where the ASIPod is related, is installed, and where the cables are running to and from the ASIPods, I would think that would be the challenge, and that would have to be tested from a ship's perspective to see where it is, because even if you run normal communication cabling inside a ship, you run into, where you have ASIPods, you run into problems. You have to optically isolate cables. You have to optically isolate RS-232 feeds because of the noise levels from the magnetic and electrical domain. So there are some challenges, I think, which probably need to be done. And I notice all of these are pure mechanical installations, so probably not truly predictive of the modern ship or some of the more modern ship designs. It's a comment rather than a question.
Yes, SPAD means you mean thruster?
Sorry?
SPAD?
Yes,
SPAD
SPAD,
means
thrusters,
thruster.
yeah.
We
Azipod
have
propulsion.
Yeah.
So the
yeah,
Azipod propulsion.
rotating thruster.
Yeah.
Right? Yeah. We have installed and we have conduct many some kind of test bed when engines on. Engines, you know, that the pump and some many motors inside the engine room. These are
mechanical motors. So.
Yeah, right. So we have conducted many situation, many test bed. So we have concluded that this magnetic field cannot make any interference to them or do not any harm from them.
In the mechanical domain, yes.
In the mechanical domain and in the interference domain.
Okay.
Yeah.
I think
we can prove as a material.
I think when you're running 4,000 and 5,000 kiloamps of energy from through to an Azipod, you got to go back and realize that a mechanical engine and a Azipod are they're two different worlds.
You mean the very big system, right? You mean?
No, an Azipod is electrical engine, electromagnetic engine which lives underneath the ship, and it has a commutator which has lots of brushes and cables, which runs to a diesel engine which has its own generator. So the engine and the electrical and the propulsion of the ship are very far from each other, and the result is that because you're transferring so much power, you're transferring a lot. You have a lot of magnetic fields and a lot of cabling issues that go along when you do a ship of that size.
Okay, next time I can show you any test result on the electric generator or electrical part.
But just a minute, you are right, because the engine or the mechanical system generates noise. The noise is composed of electromagnetic wave. So when the electromagnetic wave contact with the metal, and then they remove, because the 무슨 이론이지 아까 얘기했던 게 evanescent by the evanescent theory, if the electromagnetic wave contact with metal and very high speed removed, so the noise is removed in the metal. So our metal magnetic wave communication and the noise is not interfere with each other. So we tested several times. So in the noise graph, if we use the wireless communication, wireless communication is operate, but engine is on, and then wireless communication is off because of the noise. But this one is no problem. So no interference from the magnetic wave outside. So we can prove any times, measure several times.
Only need some any proof.
just had the problems in the past.
Okay, thank you.
Okay. Thank you for that. And that actually brings us to 31 minutes. I know we started a bit late, but I thought everyone has done their work to prepare these presentations. I wanted to allow everyone their 30 minutes. And we do have the input paper on this, which has actually been provided to us. So I think that's fantastic. Thank you for that. And now we are ending the session. So I guess we can stop the recording. Before we do that, I'm not sure who's managing that. Thank you, Jaime. You're wonderful. And we will close out session. We're a bit late now. Ernie, when do you want everybody back? We're going to be doing the MRCP review after.